the design patterns is our opportunity to collaborate, interact, gain knowledge, and today we are going to see and feel how the training course is going to be like. With that, let's begin. At the end of this session, we should be able to understand and appreciate the need of design patterns. We should be able to build some flexible design using a select design patterns. We will look at the UML diagrams, what they are, why one would use them. We will look at the Abstractfactory Pattern, the Observer Pattern, and the Mediator Pattern. So let's understand what a pattern is. When you're seeing my screen, you will see there are some diagrams in a sequence, and some of us might have played with these kind of questions and trying to figure out what is the next number or diagram or an alphabet. This is a very general problem statement in the world of aptitude tests, and this is how and therefore ability to figure out the pattern is a crucial one. Now the pattern that we have on the screen, here is a solution. One of the characteristics of the pattern are that they are easy to recognize, right? And we see them all the time. We just need to observe and you will see the patterns in the real life everywhere you look at it. And that makes them very powerful because they're observable, easily observable. The other people can also appreciate it and deduce certain logic based on it. Moreover, patterns come in handy because they are answers to some recurring problems. And because the problem is recurring, its best known solution, that is pattern, is also recurring. So you will see the yellow highlighted numbers or diagrams are the next in the sequence because we were trying to identify a pattern. Since all of us here are some sort of software developers, the next question would be, are there patterns in the software development? There are problems in the development. Can we figure out some recurring solution to these problems? And the obvious answer is yes. And it's not only just plain simple yes, it is, oh, definitely yes, and we should consider using those patterns. Because they are recurring solutions, they are very well understood by the industry, and industry has also analyzed them for their weak points and the strong points. Where should we use them, the context of the problem and the constraints, that is what can we do or not do with those patterns. Here comes our pioneers in the space of design patterns. They're called Gang of Four, and they were one of the first ones to catalog the design patterns. Now note this, these Gang of Four guys did not invent the patterns. They just analyzed the existing systems and draw commonality and catalog them, that is listed them as the design patterns. And it was a groundbreaking book, the one that they wrote, because it changed the way we think about softwares, and we then started saying, okay, so if we know the problem statement and if there is a match, we can very well pick up a design pattern from the catalog and solve the problem. And we don't have to bang our head to figure out how do I solve it and also meet all the constraints and make it maintainable. So before I move on to the next slide, note their faces, how happy they seem to be. So importance of the design patterns. Well, one of the most important part in design patterns is industry experts understand them, and so can your and my peers. and it brings up a common language for people to talk to each other when they are talking about software development. They also are based on, in recent times, something called object-oriented programming paradigm, which is the most popular methodology of developing the software. But it also comes with a downside. A downside is that many programmers and sometimes even designers falsely assume that design patterns and object-oriented paradigms are one and the same, but they are not. In general, patterns and then design patterns have nothing to do with a specific kind of programming paradigm, in this case object-oriented. Because object-oriented is more prevalent, therefore the design patterns for object-oriented world are more prevalent. Most importantly, these design patterns are tried and proven solutions to programming problems, the problems that recur. And if we choose to implement a particular design pattern to solve a particular problem, it guarantees us that the next person who's going to maintain the code understands it, because they will be able to understand the design pattern. And we also know the weaknesses and strengths of those design patterns. So should the context change, we will be re-looking at the design pattern and say whether it is still okay to use, or should we switch it to or swap it out in favor of another design pattern. Today we are going to look at a use case, a problem statement. We're going to say that let there be some sort of factory, a factory which consumes the raw material and produces the finished good. That factory could be a cement factory or a pickle factory or a cheese factory, even a chocolate factory if you like. The factory is going to get some material, some raw material. There would be some automated machines that keep track of the speed, the temperature, the ingredients and all. And the data is captured using sensors, various sensors employed in this automated system, and these sensors are going to send their input to the master control system. The master control system will look at those sensor values and operate on the data, decide what action to take, and then action is relayed to something called actuators, which may change the temperature or may change the mixture proportion. These machines operate in coordination. If one of the part fails, the operation is cannot be completed. So there needs to be communication between these entities in your factory. For example, a temperature sensor talking to the master controller, and master controller talking to maybe a furnace, an electric furnace, to either lower the temperature or increase the temperature. A real world scenario question will be, how can we build this automated system? So we'll continue with this use case and requirements. We are saying that let there be different entities that are monitoring data generated by the sensors. Each entity can take its own decision on data as well as inform to other. For example, a temperature sensor may display it to a human operator as well as send that data to the master controller. And there is a master management control room where the commands to different entities are generated, which is solely responsible for the good and safe operations. And the data from the entities is also sent back to the master management control room, where it is processed and actions can be taken. In some cases, even the audit logs can be generated. With that, moving on, here is the general depiction of how the solution would look like. There could be packaging entities, the master management control, the catalyst control, and the chemical control entity. And you see these blue diamond, they are actuators. So all these bubbles are gonna operate on actuators, and these yellow rectangles are sensors who are gonna send data to these bubbles. If you look at it, the master management control is a central entity which is responsible for the operation of this factory, where the three other entities which are separate domains, some handling chemical composition, catalysts, and packaging. But it is the master management controller system which orchestrates various operations in this. So this is going to be a general depiction. We will then come to how a non-object oriented world can program it. They will probably go by procedural system, and they will put all the functionality pertaining to management control into something called a main function. And then main function may have certain other helping procedures or child procedures, subroutines, which allow main to segment its works. Well, it may solve your problem, but it may be hard to maintain. What happens, for example, the catalyst composition needs to change. You'll have to figure out the exact procedure where it needs to change, go update that procedure, recompile your code, test it out, and then deploy it into a production system. Now, the challenge here of the procedural system is that it thinks like human brain. You know, I walk up the stairs. If I need to go to, let's say, a third floor, I know that I have to walk up to the base of the staircase or at the elevator area and do a next step, maybe start climbing up or requesting the elevator based on what we chose to do, and so on and so forth. Essentially, a procedural language is more like one looking at it from a single point of view. In this case, if a human needs to go to a third floor, a human will start thinking what he needs to do and not what needs to happen in the environment that he is living in. Such procedures would be good if you are building a very small application, maybe something that accepts the data in the single form in a web UI. But this cannot scale when we are talking about complex enterprise-wide applications, especially those applications which are to be maintained for, let's say, 5 to 7 years. In fact, what ends up happening if you write procedural programming there is you write a lot of spaghetti code. And therefore, in general, one would want to move into the object-oriented paradigm where each entity is represented by an object or set of objects, and that allows you to maintain the program in the long run. Here comes the object-oriented world's kind of introduction. With any technology, it's not going to solve all your problems just by using it. One has to be a little more intelligent as to find out how to use it. There is an old saying which goes like, the one who has a hammer thinks that every problem or everything is a nail. We will be doing good if we remember that we don't own a hammer, and if we own a hammer, not every problem is a nail. You don't have to use the same old stuff to solve any new problem. Then what problem should we be solving by having that hammer, or in this case having some known solutions? That's where need of understanding design pattern comes in. So let's talk a little bit about object-oriented on the slide. An object-oriented programmer may take a master management control unit in one object, and subsequently different entities are different objects, and one would want them to talk to each other to achieve certain use case. So as rightly noted there, once we have identified the objects, the only remaining part is to find out how they will talk to each other, communicate to each other, uh, to achieve a same common goal. In this case, the use case that we talked about. When we look at it, we definitely know that there is something missing. And what is it missing? Well, how about a change required because there is a new research coming in? Or how about I want to scale up my application? In this case, for example, I want to increase the unit production per day of my factory. In a software world, that will mean how can I make my application run faster? And most importantly, which is the life of any software, it has to evolve because the business needs change. And sometimes we add functions or features to the existing software. Let's say in case of a cement factory, I want to change my packaging from a 50 kg bag to maybe a 10 kg bag. And I also want to, let's say, change the material of the sack in which my cement gets packaged in. So in the life of a software, it is important to understand initially that a code needs to be maintainable. If I may share with you some statistics, it is very likely that a software application will spend 80% of its lifetime in the maintenance mode, where you're just making sure that the software survives in the production. Perhaps we spend about 10 to 12% of the time designing a system, and only maybe 8% time to write the code and test the code. And therefore, while building any system, one has to also consider what does it take to maintain it. And that is where, if you know the design patterns and if you apply them correctly, the answers will come naturally. Every design pattern will have, as I said, its own strength and weakness. And what matters in the maintenance mode of a software is how do we cope up with the weakness of any system. So as I said, the design patterns are kind of cataloged, right? And if you know the design pattern and if you know how to use it, you would be a better software developer. But there's a difference between knowing what a pattern is and knowing how and when to use it. If I may draw your attention to a difference between a knowledge and a wisdom. In knowledge, we'll say, oh, there is a design pattern catalog wherein there are patterns XYZ and it is to be applied in certain cases. But it is the wisdom which will tell you when exactly to use it, when you should not be using it. And generally that comes with experience. And I'm here with you to share that experience and some sort of wisdom. There is an old saying, if I may quote it here, knowledge is like knowing that tomato is a fruit, but wisdom is knowing that it is not to be put into a fruit salad. So if you look at a design pattern catalog and you find out, oh, well, there is an Abstractfactory, but if you don't know when and how to use it, that knowledge is not really useful, isn't it? You'll probably be creating more mess than you started with. And that's where we come in. We want to share with you the experience that we have in industry and knowing, for example, an Abstractfactory. What is it and how to use it and what is the consequence of using it in the maintenance mode. So with that, I am moving to the next slide. We're saying that we will model this manufacturing entity with some design patterns. For example, if you don't do it with design pattern, it will work. But then in future, when you want to extend the functionality or make it more maintainable or scalable, it will be a hard task to take up. So one also have to understand Okay, most of the time we think about building a new software. Have we thought about when the software dies? Well, I can tell you that a software dies, meaning the software is taken out of production, when it is no longer economical to maintain it. The code has become something called a spaghetti code. The original developers who developed it are no longer with that organization, and the new developers did not perhaps got the entire KT, or did get the KT but did not get their facts together, and it is cost prohibitive to add feature to that software. In such cases, the architects and the business stakeholders will want to think about building a brand new system. And if the brand new system is not developed well, the cycle repeats. Very soon the software will age. It is not beneficial to maintain, or it is a cost prohibitive to maintain that system in production. And then architects and business stakeholders will come and say, oh, they want to build a new system. So using the right solution, in this case right design patterns, extends the life of the system. And that's where it is important for us to know the design patterns and know how to use it, not only for the fresh or greenfield projects, but also for the projects under maintenance. Design patterns are generally a common language between the development organizations. For example, if you are building an Abstractfactory pattern, somewhere in the comments you will say that, well, this is a standard Abstractfactory pattern, and let's say 3 years, 4 years down the line, somebody wants to come in and in the maintenance mode, enhance it, or kind of make some changes because of maybe a business scenario changing. The person will read Abstractfactory pattern, he'll easily be able to correlate the related classes to those entities in the Abstractfactory, or any other pattern for that matter, right? That makes it very maintenance of a large enterprise scale applications moderately easy to maintain. Now, because design patterns are proven solution, you also know the consequences. Should there be in the maintenance mode, should there be a added requirement to a scenario which makes that design pattern not so lucrative, one will have an option of swapping out that design pattern in favor of some other design pattern which makes more sense. And that's where it's very important to understand how to use design patterns. Moving on, we'll talk about something called a unified modeling language. It is a diagrammatical representation of how the solution will look like. In most of the time, it is an object-oriented solution that will look like. And if I have to quote another saying, it says, a picture is worth more than 1,000 words. Same is in UML, it is worth more than maybe 1 kilo lines of code. And why it is important? Because not only the programmers, but also architects and the system engineers and the business stakeholders can understand and appreciate the design expressed in the UML. Another benefit of UML is it is programming language independent. You can have an UML and use tools to, let's say, forward engineer your UML design into a Java code or a .NET code or any other programming language that the tool supports. Talking about UML, it is a set of predefined diagrams and set of notations that one would use to show various aspects of the objects or classes. There are a set of diagrams shown on the picture, the categorization of them. Essentially, they are structural and behavioral diagrams. A structure has something to do with a static representation of the class or a package or a component. Sometimes it also shows how your component is deployed in the production system. A behavioral diagram will talk about how the runtime behavior of the program is. In that sense, one would draw an activity diagram, which is in part similar to a flow diagram, telling how program will execute, a use case diagram telling how the program will be used, a system will be used, a state diagram that talks about a state of a particular entity, so on and so forth. Now remember that not all these diagrams are useful in a given context. For example, if you are not going to do any real-time system development, you may not even worry about a timing diagram. It may not add value to your design. But there will be places where you would want to use, let's say, a sequence diagram showing how the sequence of call flows happen in a particular use case realization. For our discussions, we are not gonna do a lot of UML kind of designs or notations. So if you have not looked at in-depth UML, do not worry. We will just be drawing some block diagrams and using very minor features of the UML. Will not be going into advanced UML. So no worries if you have not looked at the UMLs. There are tools to draw these diagrams. The free ones are Argo UML, Dia, UMLet, Star UML. They are free, open source with simple user interface. Allows you to create some diagrams quite quickly. And there are enterprise level modeling software applications like an enterprise architect by Microsoft. There is also an enterprise architect by IBM. There's a Magic Draw by No Magic Corporation. And IBM has always been leading with rational rows and likes of tool sets. Now, most of the commercial softwares will allow you to do a forward engineering as well as reverse engineering. A forward engineering will allow you to convert a particular design into code, and a reverse engineering will allow you to import your code into UML. It will read the code and generate the UML diagrams for you. And what is interesting is almost all these tools, freewares as well as the paid ones, come up with a set of design pattern applications. So you can put in the, you can come into the tool and say, oh, draw me a Abstractfactory, and it will draw you an Abstractfactory, and you will end up changing only the class names. Again, tools make life easier, but what needs to happen is the user must understand how to use a tool and then how to use a design pattern that that tool is going to draw for you. With that, let's talk about the Abstractfactory. In our problem space, we are looking at maybe building a cement factory or a cheese factory. Now, do not confuse these cheese factory with Abstractfactory because the names are the same. What happens in Abstractfactory is it generates the factory classes for a one of a kind of objects. For example, if you are going to build a cement factory, an Abstractfactory will give you an actuator factory as well as the sensor factory that is applicable only to cement factory and not, let's say, a cheese factory, because the actuators and sensors in the world of cement factory will be drastically different than those for, let's say, a cheese factory or a pickle factory if you like pickle. So Abstractfactory allows you to generate the particular category of classes. In this case, an actuator for cement factory will always be generating the flow sensors or the weighing sensors for the cement factory, whereas the pickle factory will have a different kind of sensors or actuators. So depending on which factory we are building, the client will ask Abstractfactory to get you the specific factory for that problem sentence, let's say a cement factory, and then client will start using those to generate the actuators and sensors. Now an abstract factory always works with an abstract representation of the real object. In this case, it can be an interface or an abstract class. And the factories generate the concrete classes for those. In this case, for example, an abstract actuator is known to the client, but client does not know what is a furnace actuator and how to construct it. That will be constructed by the actual actuator factory. Same is the case with, let's say, a flow actuator or a temperature sensor or a flow sensor. So that's an abstract factory. Again, if you want to relate it to a real-time or real-life example in a software world, consider abstract factory as your theme in, let's say, Windows. Okay, so when you apply a theme, you just choose a different theme factory, and that theme factory will give you the actual instance of Windows, the start bars, the buttons, and the background color and all those stuff. When as a user you change your theme, the client underneath is going to change the factory implementation specific to that chosen theme, and all of a sudden you will see your buttons and bars and everything is changed, because the desktop client is going to use a different factory to render those. In the Java world, you will see a AWT or a swing toolkits being using the similar abstract factory implementation. What is the beauty of abstract factory implementation? Well, you can plug in another set of factories to the implementation, and your client does not know what's happening under the hood in the abstract factory. All the client will ask abstract factory is to get a factory of a particular kind, and that factory of a particular kind will give the real instances of the object. So thus we avoid something called ripple effect. Let's talk about a little bit about a ripple effect. A ripple effect is a need of changing one or more objects because one object changed. In this case, we have contained the ripple effect. Let's say we build another factory for a different theme. The client does not have to change. Therefore, the changes are only constrained within the abstract factory and nowhere else. So abstract factory, good if you want to change the behavior of a set of classes, and it allows you a plug and play kind of behavior if you design it right. The client does not need to change, and thus you can add more behaviors on the fly when you need them. The next page, we're going to talk about yet another pattern called an observer pattern. As the name suggests, an observer pattern will allow you to observe a particular subject or a class. A class under observation is generally named a subject. So what ends up happening is your observer will subscribe to the subject. And when there is when we say subscribe to a subject, right, it subscribes to a state change in that subject. And what ends up happening is the subject will notify back to the observer when the state that observer was interested in changes. So if you look at the next diagram on the page, it shows you some UML diagram, and you don't have to worry about the UML diagram if you don't know it. It will show you a subject and observer. A line between subject and observer shows some sort of association. The observer will attach itself to the subject, or somebody else will attach the observer to the subject. That could be your master program. An observer can be detached. An observer, when attached, gets notified when a state of a subject changes, and then observer updates itself or does some sort of update operation, and keeps listening for any future subject changes or subject state changes. In the lower half of a diagram, you will see that there is a packaging, a concrete subject, and a chemical control called a concrete observer. And when the packaging state changes, it will notify the chemical controller with an object state, with a new object's state, and the chemical control will kind of update itself with that new state, and that operation, it may tell about the change in the packaging to a master controller. With that, let's move on and talk something about a mediator pattern. Now, we talked about observer. One would relate these observers to the sensors, right? An observer will be attached to a sensor, and when the sensor's value, for example, a temperature changes, it will tell it to the observer, and then observer will tell it to probably the master controller. But then the more number of observers you have and the sensors you have, the communication paths between these observers and the master controller becomes complex, right? There are, let's say, 10 different observers, all of them telling their values or talking to the master controller. Or in some even more complex scenarios, the observers talking to each other, which will then be a computational value, and the complexity will grow exponentially. For example, 10 objects talking to each other will mean 90 independent paths in which they can talk to each other. Such code becomes quite complicated to maintain and very prone to bugs and defects to be introduced. And therefore, in general, as a good practice, we avoid multiple communication channels between multiple objects or entities interacting, because there will be so many paths of communication. The testing becomes hard, and in fact it becomes real hard. And therefore we will look at a pattern called a mediator pattern, where we limit how much objects can talk to each other, and it is achieved by something called a mediator interface. Each object, which is in this case we call them colleagues, in our cases they could be observers, and each observer who wants to communicate with another entity will not talk to that entity directly, but go through a mediator, right? It's like a person standing in a hallway, and everybody in the room, in their own room, talking to that person in the hallway, communicating the message. The person goes to the next room and delivers it to a concerned person. So let's say if you have 10 rooms and there are 10 people, one person sitting in each room, instead of one person going to 9 other doors, you talk to this person in the hallway, and that person goes to whoever the message was for. So thereby, if you have 10 objects, in earlier case we were saying 10 objects talking to each other will mean 90 independent paths. Here we are saying 10 objects, all of them will talk to a mediator and listen from mediator. All of a sudden our independent communication paths become 20, right? 10 for each, 10 paths for the observers talking to mediator, and 10 paths for mediator talking to 10 different objects. That reduces complexity. The observer that we were talking about, the object in the mediator pattern, is called a colleague because he is colleague to the mediator, and a colleague may have different concrete instances of all those people who are, or objects who are trying to talk. A mediator is an interface, so colleagues know about the mediator interface, but the actual concrete object or class may be different. And because it is interface driven, the controllers or the colleagues do not know about need to know about what the concrete mediator is. If we draw the parallel to the man standing in the corridor, in a hallway, the person sitting in the room only needs to know how to talk to that person. Maybe he can only speak in English, so you'll only talk in English. But you don't need to know the name of that person or in what shift that person is going to work and all that stuff. The person is still there. You just need to know that he can talk in English and he knows how to communicate a message to other colleague, and that's all. So in the UML depiction diagram, there is an association between a mediator and a colleague, and a mediator is extended or subclassed into a concrete mediator, and the colleagues may have one or more concrete instances of or concrete classes of the colleagues. With that, we have these three patterns that will help us solve the cement factory or a pickle factory or a cheese factory problem much easier. The mediator will talk to the central controller. The colleagues will be all sensors. The observers will be, rather the colleagues will be all the observers, and the sensors will be observed by the observer. And you have this Abstractfactory pattern which allows you to generate a specific category of sensors or actuators. And there are more design patterns to solve the majority of the problems in the software designs. And why there are so many design patterns? Because there are so many problems, and because those problems can be solved successfully by managing the constraints and optimizing the benefits. And it is an ever-growing scenario. Note that the design patterns are never ever invented. They are discovered. They're discovered through practice and then are documented. However, in recent times, in an object-oriented world, there have not been new patterns introduced because the field is quite mature now. And therefore, we as object-oriented programmers should always ask, if there is a problem, is there a solution ready-made that I can employ and speed up my development and also make the software cost-effective? And in the training that we are going to attend, that will be our focus. How can we make you efficient? How can we make you a smarter software developer and designer? And design patterns, knowing them and knowing them well, knowing how to use them, goes a long way in making one a good software developer. The design pattern, because we will be using a common terminology, are also easier to communicate. For example, in a mediator pattern, if you say colleague, people will understand what a colleague is. Or in an observer pattern, if you say subject, people will know subject is something that is being observed for the state change. More and more, the software field is maturing. It is no more an art, but it is a skill that one can learn, and a skill that will make you a better programmer. And knowing design patterns is an important skill in that spectrum. It allows you to talk to maybe your seniors, your architects, your colleagues in a common nomenclature, and it allows them also to get a feel that you understand and know what you're talking about, and you're not talking something that does not sound good or sounds foolish, if I may use that word. If you say, for example, an abstract factory and a concrete factory, it is better you know what you mean, and it is also easier for architects and the stakeholders to understand, oh, you're saying abstract factory, that means, okay, I know this problem will be solved or not solved, right? Based on whether you applied it correctly or not.